Welcome in this new recording on astronavigation, where today we will be talking about rise and set. Okay, when we talk about rise and set, the rising and setting of the sun can be seen when we take a look at the apparent daily motion of the sun. Okay, now the apparent daily motion forms a path perpendicular to the north-south pole axis, above or beyond the or beneath the celestial equator, depending on the declination. Okay, so in this case our declination will be south. Here we have our latitude, this is our co-latitude. Okay, and so the pink path is the path that is followed by the true sun. It's the apparent path. Okay, on this apparent path we have a couple of special places. The first one here being the moment when the sun rises above the celestial equator, and that means that the sun will be rising. Okay, then when after sunrise the altitude of the sun increases along this path here. It goes up and it goes up until it's at its culmination point. Okay, culmination is also called Meridian Passage. Okay, at this position the sun is at its maximum altitude. Okay, then after culmination the altitude of the sun starts going down again until the sun is on the celestial horizon, where the sun will be setting. After setting, the sun sinks deeper until it passes its lowest point, which is called the lower Meridian Passage, or lower culmination point. Okay, now what we will be doing is we will want to try to calculate our polar angle at the moment of culmination. Okay, because this polar angle will tell us something, or with this polar angle we will be able to calculate the exact moment of sunrise. Okay, voila. How will we do this? Now if we take a look at this drawing, you see that on this drawing, when the sun is on the celestial equator, that the zenithal distance, which you have here, is, I think you can all say this together, that the zenith distance will be 90 degrees. Why? Because the altitude when the sun is on the celestial equator will be 0 degrees. And 0 distance plus altitude always equals 90 degrees. Okay, voila. So when our sun is here in position X, our zenithal distance will be 90 degrees. Okay, so we see that the sun always rises in the east, so our polar angle will be east when the sun rises, and it will be west when the sun sets. Okay, the sun always sets in the east and rises in the east and sets in the west, excuse me. Okay, voila. Now if we take a look at the other triangle that we see here, being this one here, we see that there also we have an angle of 90 degrees. Now this is of less interest for us. Okay, so we will now mainly focus on this angle here, a spherical triangle, actually, not angle, spherical triangle. Okay, you know that when we have a spherical triangle where one of the sides or one of the angles is 90 degrees, that we can use the Napier method. Okay, and you have learned during the mathematical course of Mr. Buchan that according to the rules of Napier, you can represent this spherical triangle here this way. Okay, so what do? You just say, okay, my zenithal distance here is 90 degrees. And so what do I do then? I take the two adjacent sides and I subtract them from 90 degrees. So I take 90 degrees minus this. I should have corrected, it should be the zenithal distance. And then I take 90 degrees. Sorry, no, this is correct. I'm sorry, I'm mistaken. So you take this is the 90 degrees. Here you have your azimuth. Okay, so the adjacent angle or side is the azimuth here. So you subtract the azimuth from 90 degrees, and you subtract x, which is this angle here, from 90 degrees. Okay, and then you just go on chronologically. After the azimuth, the first thing that you pass by is the co-latitude. Then you have this angle here is the polar angle. So I mentioned there my polar angle. And then we have the zenithal distance, sorry, the polar angle with, the polar distance, excuse me. It's going a little bit difficult today, apparently. Our polar distance, okay? And then we can say, okay, the cosine of any of these elements is equal to the cotangent of the adjacent sides multiplied. Okay, so cotangent from adjacent side 1 multiplied by adjacent side 2. Okay, and so in this case, if we want to calculate the cosine of P, we can say, okay, this equals the cotangent of the two adjacent sides. This means we have the cotangent of the co-latitude and the cotangent of our polar angle. This is the same as the cotangent of 90 degrees minus L and the cotangent of the polar distance, okay? That we transform into the tangent of the latitude multiplied by the tangent by the declination, because our polar distance is 90 degrees minus the declination, and 90 degrees minus latitude equals our co-latitude. Okay, voila, and so we can calculate the cosine of P, of our polar angle. Okay, and so what does this tell us about the moment of sunrise and sunset? Here again on this drawing we have our polar angle, okay, which equals this arc here, okay? And so what can we do if we know the moment of meridian passage? If we can calculate this, then we know that some hours, how many hours before actually that the sun was in this position, and how many hours later that the sun will be in this position, okay? And so what should we do then? We should do nothing else but then calculating the polar angle with a formula, and then transforming the polar angle into a polar angle in time, okay? So let's say that our polar angle is, I don't know what, 150 degrees. That means that we have 10 hours that have passed, okay? Voila. Now, so if we know the moment of meridian passage is LAT 12 o'clock, that you know, okay, that is mentioned here. What should you do then? You should do something with the equation of time in order to obtain your LMT, okay? So this is meant by the equation of time, okay? And then, okay, what should you do? Then you should either add or subtract your polar angle transformed into time, okay? We know that sun rises before meridian passage, so if we want to calculate the time of sunrise, we have to subtract our polar angle in time. So in this side, we subtract, okay? We know that the setting is after meridian passage, so here we have to add, okay? Clear? Voila, so our polar angle tells us something about, if we know the time of meridian passage, our polar angle can tell us something about the exact time of sunrise and sunset, okay? But then, of course, we have to know our latitude and our declination, okay? Voila, but this will get, we'll do some exercises on this, or we'll be using this polar angle transformed into time when we'll be doing the exercises after the holidays, okay? Now, sunrise and sunset in the Nautical Almanac, conventionally, it refers to the time where the upper limb of the disk of the sun is on the visible horizon, okay? That's in the Nautical Almanac, when the upper limb of the disk is on the visible horizon, okay? Atmospheric conditions will assumed to be average, and the location is in a level on the Earth's, is in a level region on the Earth's surface, okay? Voila. Now, sunrise is when the sun's upper limb is on the visible horizon, but of course, corrections will have to be made because we know that the visible horizon is not equal to the true horizon. So 6 minutes 16 minutes for semi-diameter will have to be allowed, and in total we will see that we have to add a correction of 34 minutes for horizontal refraction. Okay. Moonrise and moonset are computed for exactly the same circumstances as sunrise and sunset, but it may occur in any time during 24-hour period. So it's very often possible that the sun will be seen during daylight and to have moonless nights. Okay. It's also possible that moonrise and moonset do not occur at a specific place on Earth on a given date. Okay, but this is all mentioned in the Nautical Almanac. Okay, voila. Now, when we talk about horizons, we know there is a distinction between the theoretical horizon and the visible horizon. Okay, the true horizon is used for calculating the theoretical sunrise, and the visible horizon is used for calculating visible or determining visible rise and set. Okay, so there is a difference between the visible horizon that we see and the location of the true horizon. Okay, this is because of the refraction in the atmosphere. Okay, now what is the location of the true horizon? The plane of the true horizon at the observer's place is actually above the visible horizon, as I told you, due to terrestrial refraction in the atmosphere, excuse me. Now, for this refraction, if you check in the Nautical Almanac, the correction tables for stars and planets, I will show you an example later on, between 0 and 10 degrees, you will see that the correction for apparent altitude is 33.8, okay, which is actually comparable to what I told you earlier, the 43 minutes that are allowed for horizontal refraction. Okay. Voila. So this is what you see here. We have our visible horizon, we have our true horizon, and we know that the difference between them due to this refraction will be 33.8. Okay. So this means that if you do an observation, you will have to subtract 33.8 from your observation because the true horizon is actually above the visible horizon. Okay. This also means that if you take a look at a star, and if you think that your star is on your visible horizon, okay, that the altitude referring to the true horizon, as you can see here, that it will be a negative altitude, being this one here. Okay. And this also means that if you see a star at an apparent altitude of 10 degrees, apparent is a reference to your visible horizon, you will see that you will have to apply corrections. Okay. And these corrections, they will have to be subtracted, as you can see here, subtracted from your altitude. Okay. If you take a look at the Nautical Almanac, then you will see there that the corrections in some cases they will have to be added, in some cases they will have to be subtracted. But that is then relative to the fact whether you do an observation of the upper limb or of the lower limb of the sun. Okay. Voila. Here you see the altitude correction tables for 0 up to 10 degrees for sun, stars, and planets. And you see here that indeed, if you have an apparent altitude of 0 degrees, that you will have to apply a correction of 33.8, which is equal to the difference that you see here between the true and the visible horizon. Okay. Now, when is the center of the sun on the true horizon? Okay. We know that the semi-diameter of the sun is 60 minutes, okay, and that the distance between the true and the visible horizon is 33.8. Okay. Now, when the sun's lower limb is at a semi-diameter above the visible horizon, we know that the center is in the true horizon. That is the moment of true sunrise or sunset. Okay. But unfortunately, on board, in most of the cases, we take observations of the sun at any time for either the upper limb or the lower limb, okay? And so this means that we will have to apply corrections for the semi-diameter, okay? They are included in the corrections in the Nautical Almanac, as you saw, and as you already did last year, we did some exercises on altitude corrections. You know that for sun and moon, they make a difference between observations for the upper limb and observations for the lower limb, okay? If you do an observation of the lower limb, then then you will always have to add a correction. If you do an observation of the upper limb, then you will always have to subtract the correction, because then the altitude that you have measured will be too big. Okay, voilà. Okay, again, this is the same thing. So we know that our sun is on the center of the sun is on the true horizon. When? Because the difference here normally is, what was it, 33.8. Okay, if we subtract 16, take your calculator and do this, then you get 17.8, and that is approximately 1 semi-diameter of the sun. Okay, so they say the sun is on the center of the sun is on the true horizon when it's approximately 1 semi-diameter above the visible horizon. Okay, but since we do corrections when the sun is either in this position, observations when the sun is either in this position or in this position, in the Nautical Almanac, this is the lower limb, this is an upper limb observation. In the Nautical Almanac, you will have to add or subtract the semi-diameter, okay? Here you will have to, with the upper limb, you will have to subtract. For the lower limb, you will have to add altitude, okay? Voila. Okay, this is again the same thing. So when the sun is with the center on the true horizon, then she is approximately 1 semi-diameter above our visible horizon, okay? And so when we observe an altitude of 17.8, which is the one that you see here, okay? And you add a semi-diameter, then you get an altitude of 33.8, but the total correction that you have to do is 33.8, so then your true altitude, sun on the center of the true horizon, will be 0 degrees, okay? Voilà, so when is the moon on the true horizon? The moon is close to the Earth, so we need to actually apply a correction also for the horizontal parallax. We need to calculate the mean value for this, for the horizontal parallax, okay? This gives us a mean correction of 4.4. Where we have an additional mean correction of 33.5. And so we know that when we have an observed altitude of an apparent altitude of 0 degrees, and then we add all these corrections, you know that when you have the apparent altitude corrections for the moon, for horizontal parallax, and the other total correction, they will also always have to be added. So when your when the moon is on your visible horizon, the true altitude will be 38 minutes, 0.9. Okay, so when the moon is on the true horizon, we can't see the sun yet. Okay, and when the moon is in our visible horizon, it's already way above the true sun. Okay, so the moon is actually, as you will see later, not a good celestial body for doing amplitudos. You don't know yet what an amplitude is yet, but this will get clearer later. Okay, you will understand when we do the next session on amplitudes. Okay, voila. Now then we have to talk a little bit about twilight. We know that the transition from day to night, it's not instantaneous, but before sunrise and after sunset, there is a specific interval of time which we call twilight. Okay, twilight is caused by light from the sun that's scattered by the Earth's atmosphere after the sun has set or before the sun has risen, setting in the night, rising in the morning. Okay, so this is represented on this diagram here. So if the sun is at sunset, then the rays of the sunlight can illuminate this point X here. Okay, but then when the sun sinks deeper down below the horizon, the sun rays cannot reach point X anymore. So what do? They go to the atmosphere, to the upper atmosphere above the Earth, where most of the sun rays will be passing through the very thin air in the upper atmosphere. But still, nevertheless, some of the sun rays will interact with the air molecules that are there, and that will scatter the sunlight in all directions. Okay. Of course, when the sun sinks even more deeper below the horizon, then the glowing that is caused by the Earth's atmosphere and the sun rays, it will fade slowly into darkness. Okay. Voilà. Now, the period of twilight is for us a very important period, so a very important time for the navigator, because in this period, the visible horizon can still be seen, okay? And so if we want to do observations, we need to see a visible horizon because we want to measure the altitude of the celestial bodies, okay? So during the twilight, the visible horizon can still be seen, but the celestial bodies in the sky, they are already bright enough to be observed by the sextant, okay? The periods of twilight, they last longer in higher latitudes than in lower latitudes. Okay, this is represented on the drawing that you see here. So you have the Earth and the Sun at its maximum declination, which is 23 degrees 0.5. Okay, circle AB, which is this one here, it's is the beginning of the twilight. Okay, there is a right angle at the sun rays. It's the plane that is at a right angle at the sun rays. Okay. Now the twilight zone is this zone here. That is the zone where there is a twilight at that moment, and this zone is 18 degrees wide. Okay. All the rest here is darkness. So here you have sunlight. In this area, you have twilight, and then more to the south, you have a period of darkness. Okay. Now I will erase this again. Now at the equator, there is almost no twilight. Okay. More to the north, the twilight takes longer. So more to these latitudes here, the twilight will take longer. At the equator, the twilight will go faster, okay? Because when the Earth turns east, the Earth turns in this direction, an observer at the equator will go faster through the twilight than more to the north. More to the north, this goes slower, okay? Voilà. And so at latitudes higher than this is a latitude of 48.5 degrees, there it will never get dark. Oh, excuse me, this is up to here. Eh? This is 48.5 degrees. Higher than 48.5 degrees, it will never get dark because you have here the twilight, and then here, this is an area where the sun doesn't set. Okay, so above the polar circle, which is at a latitude of 66.5, which is this 48.5 plus 18 gives you 66.5. Okay, there the sun never sets. Okay, voila. Okay, so again, this is represented the same way. Zone 1 here is the sun never sets. Zone 2 is the twilight zone. Okay, zone 3 is the zone where you have daylight, twilight, and night. Zone 4 is where you have twilight and night, and then here zone 5 below the latitude of what was it, 66.5, you have permanent night. Okay, voilà. Now there are several kinds of twilight. You have civil twilight, nautical twilight, and astronomical twilight. Twilight is said to begin in the morning and to end in the evening. Civil twilight, I mean, when the center of the sun is geometrically 6 degrees below the horizon. Okay, this means that all terrestrial objects are clearly distinguished. The horizon is very clearly defined, and the brightest stars are visible. Okay, Complete darkness ends prior to the beginning of morning civil twilight, and begins after the end of evening civil twilight. Okay. Then we have nautical twilight. Nautical twilight begins and ends in the morning and in the evening when the center of the sun is geometrically 12 degrees below the horizon. Okay. There you can still see general outlines of ground objects that are distinguishable at the horizon. Okay. And then when the sun goes even further down, or well, when the sun starts to cast its light on the Earth, we talk about astronomical twilight, when the center of the sun is geometrically 18 degrees below the horizon. Okay. And so before the beginning of astronomical twilight in the morning and the end of astronomical twilight in the evening, the sun does not contribute to illumination in the sky. Okay, voila. Voila, that's in a nutshell what I wanted to tell you about rise and set. Now we get to the core of this recording. How can we calculate sunset and sunrise? Okay. Now, the time of sunset and sunrise is mentioned in the Nautical Almanac on the daily pages for the sun and the moon. Okay, it's mentioned in, or you can assume that it is mentioned in local time. Okay, for the sun you get a value, one value for 3 days. For the moon you find separate values for every day. Okay, and you get 4 days per page. Okay. The LMT is given for a certain latitude, okay? But, of course, we need to do corrections. We need to do corrections for the latitude for the sun, and we need to do corrections for both latitude and longitude for the moon, okay? And so this is an extract from the Nautical Almanac. Here you see sunrise and sunset, and then moonrise and moonset. And so you see that this value for sunrise and sunset is for 3 days. The values for the moon are given for 4 days per page. Okay, why 4 days? Because the declination of the moon changes very rapidly, and so voila, you need to get more accurate values for every day. Okay. Now, sometimes if you read some books on astronavigation, there they will tell you, and okay, you don't have to go very far. If you take a look at the back of your Nautical Almanac, there they will tell you that the times mentioned for sunrise and sunset in the Nautical Almanac, that it can be considered as the universal time for this phenomenon happening in Greenwich. Okay. Now, let's say that our longitude is 30 degrees west. This we can change into time, longitude and time. This will give us 2 hours. Now, when we say, according to the Nautical Almanac, that the sun rises in Greenwich at 7:20, okay? This means that at that time in our position, it will only be 5:20, okay? So let's say this is Greenwich. The sun rises here at 7:20. But when the sun rises at Greenwich, in our position, it will only be 5:20. Because our longitude is in the west, okay? So it will take us another 2 hours before the sun, we will be in, this is LMT, so it will take us another 2 hours before in our LMT, it will be 7:20 and the sun will rise in our position, okay? So we will say, okay, LMT 7:20, and then we see, okay, this occurs at the same, or this is the same time as if we would consider that the phenomenon would happen at Greenwich. Okay, of course, by that time, when it's LMT 7:20 by us, in our location, in Greenwich, it will already be 9:20. Okay, so this will become our local meridian, and Greenwich will have gone to this position. Okay, is that clear? So basically we can assume, everybody in our college assumes that the times mentioned in the Nautical Almanac for sunset and sunrise are in LMT. Okay, but voilà, in the Nautical Almanac, they say it's considered to be universal time of the phenomenon happening and at Greenwich. But voila, I've explained to you now that this is basically the same thing. Okay, voila. Now, if we want to calculate sunrise and sunset, what should we do? From the daily page in the Nautical Almanac, we extract the LMT for the latitude, which is smaller than our observer's latitude. Okay, so let's say that we are, you can see here that in the Nautical Almanac, the sunrise is mentioned for specific latitudes. Let's say that we are at a latitude, I don't know what, of 47 degrees. Okay, what do we do then? Then we have to interpolate between 45 and 50 degrees. Okay, so we will have to interpolate between these two values here. Okay, so what do? We get the LMT for the latitude, which is just smaller, and then we get the LMT for the latitude, which is just the next numeral higher. Okay, then we calculate the difference between the two LMTs. So we calculate the difference between these two values here. And with this difference, we have to apply corrections. Okay, so we have to go to the correction table. Okay, the correction table is the table that you see here. And how do we use this correction table? Well, first, we need to see what the interval is between two consecutive latitudes mentioned on our daily page. Okay, I'll go back to my daily page again. You see here that the intervals between the latitudes, they start from 0, and then the interval is 10 degrees, then it goes to 5 degrees, and if we get more to the north, the interval gets smaller and it becomes 2 degrees. Okay, this is what they call the tabular interval. So the tabular interval is either 10 degrees or 5 degrees or 2 degrees. Okay, and that is what we need in the first place to find the correction for applying to the sunrise and sunset. Okay, so in this case, in my example there, I said, okay, let's take something between, well, let's take 50 and 45 degrees. So we have a tabular interval of 5 degrees, and the difference between these two times is excuse me, 23 minutes if I'm not mistaken. Okay, so the difference is 23 minutes. And the tabular interval is 5 degrees. So I go to my correction table. I take the correction from the 5 degrees column. What did I say? Let's say that we are, it was, what did I say, between 45 and 50 degrees. Like this, and let's say we are at 47 degrees. Okay, the difference here is 2 degrees. So we go down in the column of 5 degrees until we find 2 degrees. Okay, and then the difference between these two times, it was 23 minutes. So this is something between 20 and 25, and this will give us then a correction of 23 is closer to 25. So our correction is 9 minutes. Okay. And so what will I have to do? We'll make an exercise on that later on. I will have to add, no, in this case, subtract my 9 minutes, because in 50 degrees, we had 3 hours 50. At 45 degrees, we had a sunrise at 4:13, okay? But we are here somewhere at 47 degrees. So the correction that I obtained, it was 9 minutes. I will have to subtract that from this 4:13. So my sunrise at a latitude of 47 degrees on a specific date will be 0404. Okay? Voilà. So these are the corrections that you have to apply for sunset, or this is the method for determining sunset. Okay? Voilà. Here you can find some examples. So first of all, find the universal time for sunset on the 8th of July when your latitude is 47.28. Okay, that is between 45 and 50. So you note the times 4:31 and 4:11 for sunrise. Okay, the difference between these two times is 20 minutes. Our tabular interval is here 5 degrees, and so for the difference between 45 and 47 is 228. So let's say 2 degrees 30. And for this value with a tabular interval of 5 degrees, we get a correction of 10 minutes. Okay, 10 minutes that should be subtracted from 431 minus 10 minutes. So this gives us 421. Okay, then we have the LMT for our correct latitude. Of course, then we have to transform LMT into GMT or universal time. So we have to apply then our longitudes transferred into time. Okay, this we get from the conversion of arc to time. Okay, voilà. And so when we are in the west, Greenwich is best. So we have to add this longitude transformed into time. Okay, voilà. This is another example that you should take a look at that. Okay. Voilà. Now, for calculating moonrise and moonset, we have to, because of the rapid change of GHA and declination, the mean times of rising and setting at the Greenwich cannot be considered as the LMT for all the other meridians. Okay, the changes of position on the celestial sphere are continuous, and as moonrise and moonset occur successively at various longitudes around the Earth, the change in time is actually distributed over all longitudes. So therefore, we need to add corrections for the longitude. Okay, so basically the procedure for moonset and moonrise is the same. You first find LMT for the latitudes higher and lower than your specific latitude. You make the difference between the LMT and with this difference and your tabular interval, you find your first basic correction for LMT. Okay, and then you have to apply a second method. Okay, a second correction. Okay, now when we calculate moonrise and moonset, we will to get correct values, we will need to interpolate between either the day before the day you want to calculate, or let's say the previous day, or the next day. Okay, and depending on where you are, whether you are in the east or in the west, I'll show it to you here. When you are in the west, you have to interpolate with the next day. When you are in the east, you have to interpolate with the previous day. Okay, so this means that you have to add your longitude correction when you're in the west, and you will have to subtract your longitude correction when you're in the east. Okay, voila. So maybe it's more easy if I explain this to you with an exercise. Calculating moonrise and moonset on the 19th of November 2020 at a latitude of 51 degrees and 20 degrees 20.5. Okay, the LMT that you find, and you can check this with me, that you find in your nautical almanac, we are at a latitude of 51. 51 is between 50 and 52. So for 50 degrees latitude, we find an LMT of 1205 on the 19th and 1217 for 52 degrees. Okay, so this is actually the same procedure as we would do for the sun. Okay, now I told you that for moonrise, we have to make an interpolation with either the previous day or no. Sorry. Either the previous day or the next day. Okay, I told you that you always have to take a look at Greenwich. When you're in the west, you have to interpolate with the next day. When you're in the east, you have to interpolate with the previous day. Okay, now we are in the west, so we will make an interpolation with the next day, and after the 19th it becomes the 20th. So we take a look at the page of the 20th, and there we find for LMT these values that you see there, 1245 and 1255. Okay, now then we follow the same procedure as for these 2 days as we do for the sun. We take the difference between these LMT values. Okay, so for the 19th, this is 12 minutes. And for the 20th, this is 10 minutes. Okay, then with a tabular interval of 2 degrees and an additional 1 degree for latitude, we find a correction for the first day of 6 minutes, for the second day of 5 minutes. Okay, now in this case, the correction will have to be added. So we do 1205 plus 0.06, and here we do 1245 plus 10. So this gives plus 5, excuse me. This correction. So this gives us 1211 here for a latitude of 51 degrees and 1250 for a latitude of 51 degrees on the 20th. Okay, and what do we do then? Then we take the difference between these two times. Okay, and so the difference between these two times is 39 degrees. Okay, with this 39 degrees, we go to the second correction table. Being this one here. Okay, this is the second correction table. So we know that, I already forgot, what is the difference between these two dates? It was 39 degrees. Okay, so that is 40 degrees approximately, and our longitude was 20 degrees, so we get a correction of 2 degrees. Okay, and then I forgot how to do this. Never mind, it's all mentioned in the Nautical Almanac, so it's mentioned there, all the information is there. So for interpolating LMT for Moonrise and Moonsets is this table. What do? We should enter it with the longitude that we did correctly, and the difference between times for the given date and for the preceding date for east longitude, so that this is Greenwich, east, west, preceding date for eastern longitudes, and the following date for western longitudes. So should you forget this at the exam, it's all in your booklet. So never forget that there is a lot of valuable information available to you in the Nautical Almanac. Okay. Now the correction is to be added for western longitude and to be subtracted for eastern longitudes. So I get my correction here, which is 2 minutes. Then I go back to my schedule, and okay, what do? I take my LMT for the day for which I wanted to calculate the moonrise. LMT was 1211. Okay, this was the final LMT that I got for that date here, this one here. And so what do I have to do? I have to add the correction, okay, the 2 minutes, and this gives me then a final sunrise, moonrise time in LMT for the correct latitude and longitude of 12:30. Okay, and then we add or subtract our longitude converted into time. In this case, we are in the west, so in Greenwich it's later, so we have to add this, and then this gives us 13:34:22 as the final GMT for moonrise. Okay, voilà. So a small recapitulation for calculating, close your eyes because it's making me be dizzy. For sunset and sunrise, what do? I'll take this example here. For sunrise, you can do it at the same time for sunrise and sunset. You, when you're at a latitude between 50 and 52 degrees, you take out the tabular sunrises for the value which is just low and just high of your true latitude. Then you calculate the difference between the two of them. So 39 minus 34 gives you 5. And then with your tabular interval of 2 degrees, you go to the correction table. I'll do this with you, 2 degrees and 5 minutes. The tabular interval is 2 degrees. And what was our latitude? We were at a latitude of 43. Where is it? So 2 degrees, it's here, and 5 minutes. and we are at a latitude of 43. So this gives us a correction, if I'm not mistaken, of 2 minutes. Okay, voilà. This is a correction of 2 minutes. Voilà. And so in this case, we will have to, you always have to see which is the highest. If you are at a latitude of 50, let's say 50, what was it? 50 degrees 43, then you have to start from the value that you get for the latitude just below, okay? And then you have to see whether it's the time goes up or the time goes down. So in this case, it goes down, so you have to do 439 minus 2, and this gives you then 437, okay? Then you transform your longitude into time, and this gives you then the GMT of 2031, okay? Voila. And then for moonset and moonrise, what should you do there? You do the same thing, but because of this rapid change in declination and GHA, you have to apply an additional correction for the longitude. Okay, this correction is spread evenly over all longitudes, and so this you can find in this table that you can see here. Okay, so first you do the normal procedures as you do for the sun. You do it for 2 dates, the date that you actually want to calculate your sunrise or sunset, and then you have to interpolate with either the preceding date when you're in the east or the following date when you're in the west. You calculate the LMT for both the dates for your particular latitude. Then you take the difference between these two, as we have done here. This is taking the difference between the two, and then with that difference and your longitude, you find the second correction for longitude, and then you apply the longitude and time for obtaining the GMT. Okay, voilà. But this is just an example. After the holidays, we'll be doing a lot of exercises on this. Okay. Voilà. Then some small intermezzo on eclipses, since we're talking about the sun and the moon. And now, what are eclipses? Eclipses are astronomical events where the celestial body is partially or completely covered by another celestial object. Okay. From the Earth, we can see 2 types of eclipses, either from the sun or from the moon. Okay, they call them solar eclipses and lunar eclipses. Okay, they occur when the sun and the Earth and the moon align in a straight or an almost straight configuration. Okay. Voilà. Now, solar eclipses, they only occur during new moon. Okay. So this means when the moon moves between the Earth and the sun. I'll show you some pictures later on. Okay. And if you want to see a total solar eclipse, and the second condition is that the moon is on or very near one of its nodes. Okay. I'll explain that to you later on. Okay. What about lunar eclipses? Well, since the moon doesn't have its own light, it shines because it reflects the sun rays. Okay, and so when the light of the sun is completely blocked, then we have lunar eclipses. Okay, lunar eclipses consequentially occur when the Earth comes between the sun and the moon and blocks the sun rays from directly reaching the moon. Okay, lunar eclipses only happen at full moon. Okay, so as I told you, solar eclipses only happen at new moon. Okay, so that is when the sun is in between, when the moon is in between the sun and the Earth. Okay, and when you have new moon, they are in alignment, the 3 celestial bodies. So the sun, the moon, and the Earth are in alignment. Now, full moon lunar eclipses only happen at full moon. And when do you get full moon? Full moon appears when, again, they are sun, Earth, and moon are aligned, but now in an opposite position. Okay, and they both are on opposite sides of the world. The moon on one side, the sun on the other. Okay, so new moon, solar eclipses, the moon is between the Earth and the sun. Full moon, then you get lunar eclipses, because then the Earth is in between the Sun and the Moon, and it can block the sun rays from shining its light on the Moon. Okay. Here you see the different phases of the Moon, where we have new Moon here, new Moon, and full Moon. Okay. Full Moon can only happen at when you get lunar eclipses. New Moon can only happen, or solar eclipses can only happen when you have new Moon. Okay. Voilà. Now, another requirement to get a total eclipse is that the Moon is in one of its nodes. Okay. When is the Moon in one of its nodes? When it crosses actually the ecliptic. Okay. So this is the Sun. This is the Earth. The ecliptic is actually the apparent movement of the Sun around the Earth. And so when the Moon crosses or is in the plane of the ecliptic, then Sun, Earth, and Moon are perfectly aligned. Okay, and so this means that the Moon is not north or south of the Sun. Actually, you could say that the declination of the Sun there then is of the Moon there is then 0 degrees. Okay, so the Moon is neither north or south. Okay, and solar eclipses only happen in the hours around new Moon and when the Moon is in one of its nodes. Okay, so solar eclipses only happen when the Moon passes a lunar node during the new Moon. Okay, so this means when it is positioned between the Earth and the Sun. Okay, so what should you have? You should have the Sun, then the Moon, and then the Earth, and they should be perfectly aligned, more or less, because there is a certain period of time, a little bit of time before and a little bit of time after that the Moon is in its node, and it's only then that you can get a total solar eclipse. Okay. Voilà. Now there are two nodes. You have the ascending node and the descending node. The ascending node, ascending means going up. This is when the Moon is moving from south to north, and descending is when it's going down. This means that the Moon is moving from north to south. Okay, this is represented again here. You have the Earth, the Sun's apparent orbit around the Earth on the ecliptic. Okay, and so when the Moon passes the ecliptic, when the path of the Moon passes the plane of the ecliptic, then Earth, Sun, and Moon are perfectly aligned. Okay, this is the ascending node. The Moon is going from south to north, and this is the descending node where the Moon is going from north to south. Okay, and so there is an eclipse window, as they call it. They say the Moon should be on or about its lunar node, and voila, the window is a window of 11 degrees 38 celestial longitude. So this is this arc here, and it's during this period that you can have eclipses. Okay. Now, you'll see this during the courses of tides, that the greatest difference between high and low tide is always around new Moon and full Moon, because again, during these moon phases, the gravitational forces of the Moon and the Sun, they all combine to pull the ocean's water into the same directions, and so this may cause spring tides. Okay, this is now completely clear, because you know that when you have, as you could have seen here, when there is a new Moon or a full Moon, then the Sun is somewhere around here. Okay, and then the Sun, the Moon, and the Earth, well, depending on what type of moon you have, when this is the Earth, then you have here a new Moon, there a full Moon, and so when they both align, the gravitational forces of both the Sun and the Moon pull on the Earth, they combine and they make each other stronger, causing spring tides. Okay. Now, when we talk about eclipses, we first have to define some words like penumbra, umbra, and antumbra. Okay. Now, when objects are illuminated by an object, what happens? They cast a shadow, okay, into space, because they block the light that hits them, okay. Now, for the moon and the earth, this is also the case, okay. And so they talk about 3 types of shadows. They talk about the umbra, the antumbra, and the penumbra, okay. Now, umbra is the shadow's darkest core, okay. Now, imagine that there is a light source and there is an object casting a shadow. When you are in the umbra, okay, you will not be able to see the light source, okay, because the object that is enlightened, it blocks all the sun rays, the light rays, excuse me, okay. The penumbra is a half shadow that occurs when a light source is only partly covered by an object, and the antumbra is a lighter area of shadow that appears beyond the umbra, and that only exists when the light source has a larger diameter than the object, okay? This will get clearer when I show you these pictures here, okay? Imagine that you have a flashlight and a basketball, okay? And that you are here, an observer, standing in the umbra, the shadow of the ball, okay? What you see then is the observer's view. You can only see the basketball because the light source is smaller than the object that is blocking the light rays, okay? So we have a punctual light source, and this creates only an umbra, okay? So the gray shaded part here is the umbra, okay? Now, let's say that you have a small light bulb. So this means a light source of a larger surface area and a diameter smaller than the object casting the shadow. Here you create 2 shadows, okay? You have first the umbra and the penumbra. If the observer would be in the umbra, he would be seeing this here. But when the observer is in the penumbra, okay, then he can still see quite a small part of the light bulb, okay? And then the third situation, where you have a very big light bulb, or when your light source is very far away from the object that blocks the light rays, then you have here an umbra, a penumbra, and again an antumbra. This is the antumbra. This is like a shadow of a shadow, okay? So if the diameter of the light source exceeds the object, the third kind of shadow appears at a certain distance from the object, and this is called the antumbra, and this is the side, the side that or the view, let's say, that the observer will have when he is standing in the antumbra. He will see both the object and the light bulb that is enlightening the basketball, okay? Now, the type of shadow is closely related to the types of solar eclipses that you have, okay? You have partial eclipses, annular eclipses, and total eclipses, okay? Now, a total eclipse, I can already tell you that now, a total eclipse will be when you are, as an observer, well, no, this should be like this, in the umbra. A partial will be when you're in the penumbra, and an annular eclipse will happen when you, as an observer, are in the antumbra. Okay, we are not talking about solar eclipses. Okay, so if the sun, you know that solar eclipses only pass when the moon passes between the sun and the earth. Okay, and so what happens then? This is your light source, LS, and this is the basketball. Okay, so what happens? The sun's light rays are blocked by the moon, and so they cause here an umbra. Okay, but since the light source is bigger, it also causes a penumbra. Okay, and so the people standing in the umbra zone here, they see a complete total solar eclipse. The people standing in the penumbra, they see a partial eclipse. Okay. Voilà. So again, these are the different types of shadow, the umbra and the penumbra. Okay. And so they say that in the darkest point here on Earth, the eclipse is almost as dark as night. In the darkest point of the eclipse, it's almost as dark as night. Okay. Now, when the object is further away from the Earth, when the Sun is at its furthest point from the Earth in its apogee, what can happen then? Then the Sun will be blocked by the Moon. It will cause a shadow up to here, and then it will stop. This is the umbra. But since the Earth is so far away, there's a possibility to create this third type of shadow, and this third type of shadow that is called the antumbra, as you can see here. Okay, and so people standing in the antumbra, they don't see a total solar eclipse, but what do they see? They see an annular solar eclipse. So they see both the light bulb and the basketball. They see both the Sun and the Moon. Okay, voilà. And so when you are standing in the penumbra, when the Sun and the Moon and the Earth don't perfectly align, then okay, then you see nobody can be standing here. You can't have total solar eclipses. You can only be standing here somewhere on the Earth in the penumbra of the Moon, where you will only see a partial solar eclipse. Okay. So this is again the same thing. The Moon, the moonlight is blocked by the sunlight is blocked by the Moon. It creates an umbra and an antumbra. In the umbra, you will get total solar eclipse. In the penumbra, you will get a partial eclipse. Okay. And then when the Moon is at its furthest point away from the Sun, then there is a possibility to create this additional third shadow, which is called the antumbra, and people standing in this antumbra, they will see an annular eclipse. Okay. Now, what about the lunar eclipses? Well, lunar eclipses, when can they occur? They can only occur when the Sun and the Earth and the Moon are again in a straight line, but Moon and Sun are both on different sides of the Earth. Okay, and so what happens? This now it's the Earth that is casting, that is illuminated by the Sun, that blocks the sunlight, and that is casting a shadow. Okay. Now, when the Moon is in the darkest part, when the Moon is in the umbra, then we see a total lunar eclipse. Okay. When the Moon is in the penumbra, then we see a partial lunar eclipse. Okay. In this situation, the Moon is in the penumbra, in the penumbra, and then we see a partial lunar eclipse. Okay. So part of the Moon here dips into the Earth's umbra, but the deepest part of the shadow, and so this will give a partial lunar eclipse. Okay. Partial lunar eclipse when the Moon is half in the umbra, half in the penumbra. Okay. Voila. So for the Moon, we have total lunar eclipses when the Moon is in the umbra, and when the Moon is half in the umbra, half in the penumbra, then we have partial lunar eclipses. Okay. Now, the solar eclipses, they occur in cycles. They call them ellipse cycles. So this means that the eclipse occurs the same time of the year in the same lunar node and at the same distance from Earth. The most famous cycle that they have discovered is the Cyrus Cycle. It was already used by ancient Babylonians to predict actually the lunar eclipses. It's a cycle of 56,000 approximately days and around approximately 18 years. Okay, and it occurs to the 3 lunar cycles that we already know, because of the fact that we have a lunar month, which is the time from one new moon to the next. Then we have an anomalistic month, which is the time from perigee to perigee. Perigee is the closest point of the Moon's orbit to the Earth. And then we have a draconic month, which is the time from one lunar node to another. Okay, where the lunar nodes are the places where the motion of the moon intersects with the ecliptic. Okay, voilà, so that's it for this recording. Should you have any questions, don't hesitate to ask them. I'll be available during the scheduled courses in the collaborative classroom. Okay, good luck.